Alright, we're going to pick up right where we left off in the last video, and we're going to look at the frequency response of op-amps. So oftentimes in everything electrical engineering, you're just going to hear that some devices, it's got some magic in it. And we really want to ask ourselves, well, are op-amps really these magical devices? Are we using some magician to get our output voltage? Are we summoning the Dark Lord? No, the answer is no, they're not. Nor are they ideal. Often is the case, always is the case, that our input impedance is not infinite, our output impedance is not equal to zero. We don't have this infinite open loop gain, and we have a finite bandwidth, which really means that the op-amp responds differently at different frequencies. So if we consider the Bode plot of an op-amp, and we look at the open loop gain, AOL, so we know with Bode plots we're going to be working in the dB scale. So in the case of our open loop gain, looking at the dB value for that, it's equal to 20 log 10, and then we have the absolute value of the open loop gain as a function of the frequency. And then horizontally here we are varying the frequency. So what we end up getting is a relatively flat gain for most frequencies until we hit some break frequency. And that break frequency is going to be given by F subscript BOL, so the break frequency of the open loop gain. But prior to that break frequency, we pretty much assume that our open loop gain is equal to 20 log 10, and then the absolute value of the open loop gain at zero frequency. It will deviate a little bit, but this value is pretty safe to use until you get to that break frequency. After you get to this break frequency, you usually see a decline in the open loop gain, and it's usually this minus 20 dB per decade decline. And that'll go until you get to some frequency FT. I always like to call that the termination frequency because your op-amp is pretty much terminated at that point. You're not getting much out of it. But we model this decline as the equation here. So we have the open loop gain at the DC case, and then we have 1 plus J times the ratio of the frequency divided by the break frequency. Now we can define something called the gain bandwidth product, and that's going to be equal to the open loop gain times the break frequency. And that's actually the value that we use for FT. Now let's consider a non-inverting op-amp. Normally we'd say with the negative feedback present that the input voltages at the terminals for the op-amp are equal, and the input currents or output currents from the input of the op-amp are equal to zero. From this, we can simply say that V minus is equal to our source voltage, Vs, and from that, we can arrive at this KCL right here. We get our output voltage equal to the source voltage times 1 plus R2 divided by R1, and we would expect that at all frequencies in a beginner course. But now that we know that the frequency can mess with the op-amp a little bit, we know that this isn't the case anymore. Instead, what we're going to say is that the output voltage is equal to the open loop gain as a function of frequency times the differential input voltage, which may look a little bit familiar. Now we can say that the voltage over R1 is equal to the output voltage, and then we have this voltage divider here with R1 and R2. Now let's just name a variable beta that's going to be equal to R1 divided by R1 plus R2, so that VR1, or the voltage over this resistor right here, that's going to be equal to beta times V out, or V naught. So let's set up a KVL from the input. So we're going to say that the source voltage minus the differential voltage right here, minus the voltage over R1, that's going to be equal to 0. And we know that the voltage over R1 is equal to beta times the output voltage, and this whole term is equal to 0. Now we know our differential input voltage, VID, that's going to be equal to the output voltage divided by the open loop gain as a function of frequency. We pull that from this equation, and that allows us to set up this equation here where we have our source voltage, our output voltage, and then the terms that we've previously defined. Now we're going to define the output voltage divided by the source voltage as something called the closed loop gain, or A subscript CL. So from the algebra up here, we can just manipulate that to get our value for the closed loop gain. And for zero frequency, or the DC case, we would expect the open loop gain as a function of frequency simply equal to the DC open loop gain. Now if that open loop gain is quite large, as we expect it to be, then the closed loop gain is approximately equal to 1 over beta, which is equal to 1 plus R2 divided by R1. Then our output voltage is equal to our source voltage multiplied by 1 plus R2 divided by R1. Looks familiar, so it seems like we're on the right track. But let's look into this closed loop gain So if we consider the open loop gain as a function of frequency, we can define the closed loop gain also as a function of frequency. And if we're past that break frequency, we know we can model it like this. So what we can do, we can take this equation and represent it like this, plug in our open loop gain as a function of frequency to arrive at this kind of messy looking term here, which we can make even messier. Now we can continue through with the algebra to eventually arrive at this bottom term here. I've tried to lay it out step by step the way that I did it. If it's confusing, leave a comment and I'll address it. While you're leaving a comment, like the video and subscribe. Helps the YouTube algorithm. But nevertheless, we can say that the closed loop gain as a function of frequency is equal to this messy term here. And we can recall what our open loop gain is as a function of frequency that we previously defined. So now we're going to introduce this DC closed loop gain term, and we just set the open loop gain to that DC case. Now from this, we can actually define something called the break frequency for the closed loop. It's going to be equal to the open loop frequency break. And then we have this open loop gain in the DC case multiplied by beta plus 1. And that allows us to clean things up a little bit and say that the closed loop gain as a function of frequency is equal to the DC closed loop gain. And then in the denominator, we have 1 plus j. And now we have the frequency divided by the closed loop frequency break. So the closed loop and open loop gains in term of frequency look fairly similar. At least that's what we try to achieve. But there is one thing to notice with this circuit, that the break frequency, especially for the closed loop case, that's dependent on beta. And beta was R1 divided by R1 plus R2. And this was circuit dependent. Right, so what does that tell us? Well, if we change the values of the resistor in our circuit, just the resistors, we change how the whole thing acts depending on some frequency. So what we can do here is actually plot the open loop gain and then the closed loop gain here in red, but we can plot that for different beta values. So what you can see is as you take beta from 0.01 to 0.1, you actually extend the case of where your break frequency is. So you start here, so you have kind of this larger bandwidth to work with depending how you set up beta. And maybe you need a certain bandwidth to work with, so you know how to limit your resistors to work with the frequencies you might expect in your system. So what have we learned from all this? Are op amps these magical devices? No, they're not. There's no magic inside of them. In the next video, we'll look at some more limitations of op amps, and then we'll move on to a new component, so that's always exciting. We'll see you there.